Good morning, friends. My name is Professor Pankaj S. Pawar, working as Assistant Professor in PS Modern College of Engineering, Pune. Today we'll go for the basic laws of heat transfer related with the conduction, convection, and radiation. So we'll recall from thermodynamics that we have the various forms of energies, and these energies can be transferred from one form to another form. Likewise, heat is also one of the form of energy, and that can be transferred from one point to other point when temperature difference exists. So if the temperature difference is present, there will be heat flow by any of the mode, that is conduction, convection, or radiation, or all the three modes can operate simultaneously. So we'll have the basic laws which governs this three mode of heat transfer that we'll discuss in this lecture. So we have the first law related with the conduction. As we know, conduction is mode of heat transfer which happens because of the movement of free electrons and the lattice vibration in case of solids. And so this conduction happens in solids, liquids, gases by various phenomena. So we have the basic law related with this heat conduction, which is given by the Joseph Fourier. And there are some assumptions which are taken into account in this Fourier's law of heat conduction. So first assumption is heat flow is assumed as a unidirectional, and also assume that heat flow is under the steady state conditions. Next is the temperature gradient is assumed as a linear and constant. There is no internal heat generation within the system. And last one is the material is assumed as a homogeneous and isotropic. So steady state means the temperature will remain will not going to change with respect to time, that is steady state condition. And the isotropic material means properties will remain same in all the directions of the material. So these are some basic assumptions while deriving the Fourier's law of heat conduction. Now we'll go for the Fourier's law of heat conduction statement. Fourier's law states that the rate of heat transfer through a homogeneous material is proportional to negative gradient in the temperature, and it is proportional to the area normal to that gradient through which that heat flows. So let's consider one plane wall is present here. So we can observe here one plane wall whose thickness is dx, and heat is going to flow from the left side to right side. So here the area normal to this flow in left to right direction is A. Temperature on the left side is T1. Temperature on the right side of the wall is T2. Here T1 is greater than T2. So heat flow from left side to right side because of this temperature difference. Now what's the Fourier's law states? The heat transfer Q is proportional to area, this A, and temperature difference, and divided by thickness of that plane wall, which is nothing but the temperature gradient. So Q is directly proportional to area as well as directly proportional to negative temperature gradient. So the equation can be derived from this as Q is equal to minus K dt by dx, where K is nothing but the constant assumed here for this proportionality. So K is thermal conductivity of this material which is considered for this plane wall. So this is a general equation for heat flow in one direction according to Fourier's law, that is Q is equal to minus Ka dt by dx. So here Q is nothing but the rate of heat transfer in watts. A is the area normal to heat flow in meter square. Then dt is the temperature difference across the plane wall, T1 minus T2 in degree centigrade or Kelvin. Tx is nothing but the thickness of the plane wall in meter. Dt by dx is the temperature gradient across the plane wall in Kelvin per meter. And K is the thermal conductivity of that material of the plane wall, whose value or unit is in watt per meter degree centigrade or watt per meter Kelvin. It is one and the same. Now here there are some relation between heat transfer by conduction and this right side of this equation. So you can observe here, as the thermal conductivity of the material increases, the rate of heat transfer by conduction is going to increase. Also, as area normal to heat flow increases, the rate of heat transfer by conduction increases. As temperature difference across the plane wall increases, heat transfer by conduction increases. And one more thing, the heat transfer rate by conduction is inversely proportional to thickness. So as temperature, as this dx increases, thickness of the wall increases, the heat transfer by conduction is going to decrease. So these are some relations. As K increases, Q increases. As area increases, Q increases. As dt, temperature difference increases, Q increases. As thickness dx increases, the heat transfer rate by conduction decreases. So there is one important property here regarding conduction, that is thermal conductivity. So what is that? Thermal conductivity is nothing but the ability of material to conduct the heat, as like specific heat is nothing but the ability of material to store the heat in the material. Similar to that, thermal conductivity shows you the ability of material to conduct the heat. Now here, what is thermal conductivity? It is the amount of heat flow rate per unit area normal to the direction of heat flow through unit thickness of material per unit temperature difference. So here, if you assume area normal to heat flow is 1 meter square, temperature difference dt, that is T1 minus T2 as 1 degree centigrade, and the thickness of the plane wall as 1 meter. So amount of heat transferred for this configuration of plane wall is nothing but the thermal conductivity of material. Let's consider we have a steel thermal conductivity as 80 watt per meter degree centigrade. So what it indicates, for the unit area, unit temperature difference and unit thickness of the plane wall, this steel material plane wall will conduct 80 watt amount from the left side to right side. So thermal conductivity, if you have very high, that material is a good conductor for heat flow, and if the thermal conductivity is less, that material will be the bad conductor for heat flow, which is also known as an insulator. So we have some materials like copper, which is having thermal conductivity about 400 watt per meter degree centigrade, and aluminium about 237 watt per meter degree centigrade. Likewise, we have the diamond, which is a non-metal having thermal conductivity value as a 2300 watt per meter degree centigrade. So these are some thermal conductivity values of the material. Unit of the thermal conductivity is nothing but the watt per meter Kelvin or watt per meter degree centigrade. So thermal conductivity is important property for heat conduction. So it should be very high for heat conduction and it should be very low for the uh, reduction of heat transfer. Now we have the next mode of heat transfer, that is convection. Convection is nothing but the conduction with fluid motion. So we have the two mode of heat transfer under the convection. One is the free convection, which is also known as a natural convection, and second one is the forced convection. In free convection, heat transfer occurs because of the density difference of the fluid, and in case of forced convection, heat transfer occurs because of the uh, some external sources like pumps, blowers, fans, likewise. So Newton's law of cooling is given by Sir Isaac Newton. Here are some examples of hot egg and cold soda where heat transfer by natural convection takes place. So Newton's law of cooling we are going to discuss here. So Newton's law of cooling states that convective heat transfer is proportional to the surface area perpendicular to that heat flow direction and the temperature difference of the plane wall surface and surrounding fluid temperature which is in contact with that surface. So here you can observe that heat air flows from the left side to right side over the plane wall whose temperature is Ts, surface area is As, and surrounding air temperature is the T infinity. So Ts is greater than T infinity here. So this hot plate by the time will become cool because this air at T infinity will take away the heat from this plane wall and the temperature will be equal to the surrounding temperature. When Ts is equal to T infinity, there will not be heat transfer by convection here. So conduction with fluid motion is nothing but the convection. So here you can observe Q is directly proportional to As surface area, also directly proportional to temperature difference. So if the surface area is more, heat transfer by convection will be more. If the temperature difference, that is surface temperature and T infinity, it is more, the heat transfer rate by convection will be more. So Q is proportional here. So we have the equation for Newton's law of cooling for convective heat transfer as Q is equal to H into As into delta T, that is Ts minus T infinity, where Q is the convective heat transfer rate in watts. As is the surface area of the plate in meter square. Ts is the surface area, surface temperature in degree centigrade or Kelvin. T infinity is the fluid temperature surrounding to that plate in degree centigrade or Kelvin. And H is the constant of proportionality in Newton's law of cooling, which is also called as heat transfer coefficient, and unit is in watt per meter square degree centigrade or watt per meter square Kelvin. So here this H is function of various parameters, like H is depending on uh, density of the fluid, then velocity of the fluid under motion, then L by D ratio, then this viscosity of the fluid, Cp of the fluid, and thermal conductivity of the that fluid under consideration. So we have the various values of heat transfer. So we can observe for natural convection with steel air we have the H4 to 25, and for steel liquids we have the 10 to 900 watt per meter square Kelvin. These values for the natural convection. And for forced convection with different fluids like air, liquid, boiling, and condensation of vapors, we have this type H values. So we can observe for during condensation or phase change process in boiling and condensation, we have the very high value of heat transfer coefficient H. So this is related with the Newton's law of cooling. Now next to this we have the Stefan Boltzmann law of radiation. We have this two Stefan and Boltzmann which derived this law. So this Stefan's law describes the intensity of thermal radiation emitted by matter in terms of that matter's temperature, and it is named after the Joseph Stefan who derived this relation, and Boltzmann who derived this law theoretically. So here we have the different wavelength values we can observe here for the electromagnetic waves. So for the microwave you can observe the value is 10 raised to 2 to 10 raised to 4. So when the value lies in between zero point 0.1 to 100 micron, that particular wavelength is nothing but for the thermal radiation. And in case of heat transfer we are interested only in this range. So as the that wavelength decreases, you can observe the rays, ultraviolet rays, x-rays or gamma rays are there. So infrared, like this. So zero point 0.1 to 100 micron, this is the range where this wavelength for thermal radiation lies. So Stefan Boltzmann law states that the total energy radiated per unit area per unit time is directly proportional to fourth power of the black body temperature or body temperature we have. So QB, that is energy radiated by that black body, is directly proportional to absolute temperature of fourth power of absolute temperature. And we have this equation here, QB is equal to epsilon into surface area of that wall, then sigma and T raised to 4. So sigma is constant in this Stefan Boltzmann law of radiation, and his whose value is which is also known as a Stefan Boltzmann constant. And here you can observe QB is the total energy radiated per unit area by the body in watts. T is the absolute temperature of the body in Kelvin. So AS is the surface area of the that wall in meter square, and emissivity epsilon is the emissivity of the that surface. So this emissivity value for the black body, it will be equal to 1, and for the non-black bodies it lies in between 0 to 1. Emissivity is nothing but the ratio of heat transfer by the body divided by heat transfer by the black body at same temperature. So epsilon value will be 1 for the black body, and for non-black it will be 0 to 1. So for black body this epsilon will be 1, so QB will be AS into sigma into T raised to 4. So sigma is Stefan Boltzmann constant whose standard value is 5.67 into 10 raised to minus 8 watt per meter square Kelvin raised to 4. Now this is the equation for Stefan Boltzmann law of the radiation. We have the different laws related with the radiation also, like we have the Planck's law, then we have the Kirchhoff's law. All these laws are related with this steep radiation mode of heat transfer. This radiation mode of heat transfer is uh, not requiring any uh, medium for the heat transfer. This radiation is going to happen without media also. Likewise, example, whatever the sun's energy is there, that energy is going to reach the earth's surface by this radiation mode of heat transfer only. So these are the three laws related with the conduction, convection and radiation mode of heat transfer. So thank you. We'll go for the next topic regarding the heat transfer in next lecture. Thank you.